Now that we've performed our model fits, it's helpful to have some more information on fitting parameters and the statistical significance of those. They'll help us to make decisions about which models fit the best beyond what we can just see visually here in the figures window. I'll also output some confidence intervals for the individual parameter fits. So I'm going to, just for example, show you 75th, 85th, and 95th percentiles. And fname is the name of the file that we'll be saving. And I'll run this section of code, which will give us the mean square error and residual standard error for the different fits. So if I go back into my working folder, I'll find an Excel file called parameter fits. And we'll notice that we've got the mean square error and residual standard error for each of the model fits that was successful. In this case, we've got 6 successful model fits. Close that. We go back to our R code. I can then add successive tabs, one for each of the different model fits we've achieved. So I'll highlight that code and run it. Now if I go back to that same parameter fits file, I'll find that now I've got multiple tabs, one for each model that successfully fit to the tracer data. So if I go under model A, I've got the estimates of the volume fraction of the first tanks in series reactor and the number of tanks, which we looked at earlier. We can also see the p-value. We'll notice that these are very, very small p-values to the negative 77th and 10 to the negative 30th. So this lets us know that both of these fitting parameters are statistically significant. If I look at model B, with the exception of the dead space fitting parameter, which had an estimate of 0, so that wasn't statistically significant. That didn't help us achieve a better fit. All of the other fitting parameters did end up being statistically significant. Same thing with model D, statistically significant. If we look at model E, a little bit different, 0.967, that would not be statistically significant at a 0.05 significance level, or 0.28, again, that dead space did not end up being statistically significant. And one way to tell is just if your confidence interval includes 0. So if we look at our 2.5 percentile and 97.5 percentile, that's the 95% confidence interval. We find that that includes numbers less than 0. So 0 is included in that range, letting us know that those parameters don't add more value in explaining the variation observed in the tracer. So this is probably not a good model to use because we have all these additional fitting parameters that don't provide additional benefit. If we look at model H, all low p-values, and if we look at model I, we have some p-values that are quite large. And so that would lead us to believe that model I and model E are probably not good models for us to use because they have more fitting parameters and we really need to explain what's going on in the data. So that's one Excel file that gets output. The next one will output the individual model fits that we have here. Again, these red lines that we've seen in each of the plots. So this section of code will solve for the value for thetas of 0 to 3 with steps of 0.1. So if I go ahead and run this section of the code right here, it will create for me a new Excel file. So if I go back in, I'll find the model output file. Again, my file name was modeloutput.xlsx. So if I find my model output, and when that loads, I find that I've got theta versus each of the different model types. So this is helpful if you want to go ahead and take these, create plots. You can plot those against your tracer data. And so this is helpful outputting it to Excel so it's more easy to manipulate and make figures. However, in the next video, I will also show you how to make figures using R.